Have you ever wondered what makes Goroutines in Go so uniquely lightweight and efficient? It all comes down to user space scheduling and Go's clever MN scheduler. But what exactly does that mean, and why is it so powerful? What is user space scheduling? Imagine a world where your application could run thousands of concurrent tasks without involving the operating system's kernel. With Goroutines, Go achieves this through user space scheduling. But why does avoiding the OS matter so much? OS-level context switching, the process where the CPU switches from one thread to another, can be slow and costly. Each switch requires saving and restoring a substantial amount of state information, leading to higher latency. This is where Go's user space scheduling steps in as a game changer. How does the MN scheduler work? The Go runtime operates an MN scheduler, which maps M Goroutines to N OS threads. Instead of needing one thread for every concurrent task, Go can manage hundreds or even thousands of Goroutines on just a handful of threads. But how is this possible? The MN model allows the Shock Go runtime to handle scheduling itself, efficiently controlling how and when Goroutines are executed. This design skips over the kernel's involvement and enables the runtime to make context switches within user space, cutting down on overhead and freeing up CPU resources for actual work rather than administrative tasks. Why does this reduce overhead? OS threads require kernel intervention for creation, management, and switching, leading to system calls and context switching delays. By contrast, Goroutines switch in user space. When a Goroutine needs to yield control or wait for I/O, the Go runtime can pause it without any system calls, maintaining the context internally and resuming it later. This minimizes the heavy lifting typically managed by the OS and makes context switching nearly instantaneous. How can thousands of Goroutines run on just a few OS threads? With user space scheduling, the Go runtime can run a multitude of lightweight Goroutines, scheduling them across fewer threads through an intelligent balancing act. This involves techniques like work stealing, where idle threads pick up tasks from busier threads to ensure optimal utilization. This clever approach keeps CPU cores busy and reduces the need for idle time or excess thread creation. What does this mean for developers? The result is a system that can support massive concurrency with minimal memory and CPU overhead. Developers don't have to worry about the complexities of thread management or the performance hits from OS-level scheduling. Instead, they can create highly concurrent applications with the confidence that Go's user space scheduler is handling it all efficiently behind the scenes. So, why does this matter? Because user space scheduling in Go is not just a technical detail. It's a fundamental reason why Go is favored for building scalable, high concurrency applications that need to handle thousands of tasks seamlessly and efficiently.